Logarithms. Okay, logarithms are extremely useful. The book I mentioned that I had for E actually talks a lot about logarithms because that's where it came from. Okay, the logarithms are inverses of exponentials. Logarithms have two really, really good uses. The one that we will do in here, the one that we use almost exclusively, is for solving exponential equations. Okay, logarithms are used for solving exponential equations. When you want to get the exponent and there is no other way to solve it, you use a logarithm. They are extremely useful for that. They will let you solve things that you could not solve in any other way. Okay, they really are. That's what they're used for. The other thing that they are used for really used for that works really awesome is they are used in statistics. It's really kind of interesting is that you can collect data, and sometimes the data doesn't fit what you want it to do for looking at it. And you can do what's called naturalizing the data, which means you take the logarithm of all your data and you use the logarithms of all that data rather than the data itself to analyze the actual data, and it works. It surprised me when we did it in my stats class in college, and it worked just fine. Very interesting. You can take something that doesn't fit a bell curve, that you can't really analyze in that way, naturalize the data, and it does. And you can use the naturalized data, interpret that data, and use that information to talk about the original data that you collected. Just kind of an odd thing. It's a way of just saying, hey, we can't work with this, let's change it so we can work with it. But what we get from here, we can use for our original stuff. It's really kind of nice to be able to do that sometimes, just kind of mess around with it. So one of the first things that you have up there on the list is the inversing of logarithms and exponentials. This is really important. That is called the looping method, okay? Being able to go back and forth between a logarithm and an exponential is extremely useful when you're trying to solve them. Particularly if you have an odd-based logarithm, you can do that. Really, it works well. Taking a logarithm, rewriting it as an exponential. The big thing you want to remember when you're doing that is that the base of your logarithm is the base of your exponential. Okay, that's how I remember which one's which. And then the other two parts trade sides. Trade what they're attached to. This is log base a of y is x. This is a to the x equals y. That's what a logarithm is. A logarithm is just saying, hey, what number do we raise the power of a to get that? Okay. Now, there are two kinds of logarithms here. There are a log with no base on it. That's log base 10. That is what one of the ones your calculator has. If you look and you see log, it has no base. That is log base 10. That is the common logarithm. We will not use that in here unless we have 10 to some power. That is the only reason we will use that in here. That is what you use almost exclusively in Algebra 2. We are going to change that. We are going to use the natural logarithm, which is log base e. When you see ln of x is the natural log of x. That is log base e. That's what we're going to use. And you have an ln button on your calculator. That is the natural log button. We'll just take the natural log of everything. Does it really matter when you're using logarithms? No, because it does not matter the base of logarithm that you use. You will still end up with the same number in the end. But we're switching over to natural logs because that's what we're going to do. And the higher up you go in math, the less you use log base 10, the more you use natural log. Just like you're going to see a lot more exponentials base e, where you have e as your base of your exponential. You're going to start seeing that more and more. When you get to calculus, it is not exclusively, but almost exclusively e to some power or natural logarithms. And so you're going to have to get comfortable with using those. Just as an aside, the mathematics club at Humboldt State was called the Natural Loggers.
Oh, nice.
That's what I was going to put in. Okay. Now, this first one is really just switching them back and forth. going back and forth between exponential equations and logarithmic equations, and that's it. It is an extremely handy tool to be able to do this. It lets you solve problems very easily this way. So I have 1.2 cubed is equal to m. Now I'm not solving for m, because if I were solving for m, what would I do? I'd take 1.2 on my calculator and cube it. Okay, that's what I would do. I'm not solving for m. The idea is to rewrite this as a logarithm. It's really actually a lot easier than it looks. The base of my exponential is 1.2. The base of my logarithm is 1.2. And then what my exponential is equal to is what I'm taking the log of, and that's equal to the power on my base. Okay, this is looping. Okay, you did this last year. This is part of how you solve some of the problems. Same thing on this one here. This is log base a, so that means I'm going to have a to the 5th power equals 4. And this is how you would solve something like this. What's my base? Rewrite it as an exponential, and then this is easy to do. Take the 5th root of both sides. A is the 5th root of 4. It would be an easy one to solve, but that's what we're doing. That's part of the reason you want to be able to do this, is you can take something you can't do and make it something you can do. E to the b is 9. This would be log base e, because of the base e, which would be our natural log. Sorry. So I get ln, natural log, of 9 is equal to b. Because it's natural log, because that is log base e. What is the base of my log here? It's 10 because it's not there. So this would be 10 to the 5th is equal to a. What's the base of my logarithm here? E. So this would be e to the x is equal to 4. Piece of cake. Okay. Like I said, we're going to use e and natural log an awful lot here to come up with those buttons. Okay. And I like it too because I only have to write 2 letters instead of 3 letters. ln instead of log. Right? You know mathematicians are extremely lazy when it comes to the writing, right?
Oh, I thought you were just going to stop at extremely lazy.
Well, that too. You know, professional mathematicians are one of the few people that get paid for sitting around and thinking. Without actually doing something, because they do 80 to 90% of their work in their head. So professional mathematicians, people that work as mathematicians, do an awful lot of work while taking walks alongside the lake or laying in a hammock and things like that. They actually get paid for doing that. They are working. It's just all up here in their head. It's not like they're writing down and taking notes. Now, they do have to write things down. They do have to work things out. They do have to do it. But a lot of their work is done in between their ears when they're doing the work. So they get paid for literally sitting around looking like they're doing nothing. They're not, but that's what it looks like. It's actually kind of cool, but you have to be up there pretty good. Okay, find the exact value of the calculator. Here's the problem. Okay. You have no log base 2 on your calculator. You do not have a button that lets you take log base 2 on your calculator. You can't. There is no button that lets you do that on your calculator. So you have to figure something else out. You got to figure out something else out. Now with these ones, it's not so bad. It says to do it without a calculator. The idea is we want to figure out the easiest way to do this. Rewrite 16 as some power of 2. Okay, rewrite 16 as some power of 2. So this is log base 2 of 2 to what power? 4. To the 4th power. Which means our answer is 4. If the base of our logarithm and the base of the exponent we're taking the log over the same, it's just the power. Well, it's not really cross them out. Technically what you're doing, and we haven't gotten there because we're going to talk more about rules of logarithms next time, is you apply some of the rules of logarithms. But that's what this basically the rule is. If these 2 numbers are the same, your answer is the power. So on the next one here, I have log base 3 of 3 to what power? Negative 3. Because the negative means it makes it 1 over. The 3 gives me the 27th. So my answer would be negative 3. Next one's a little trickier. Log base root 2 of root 2 to what power? Well, 4 is 2 to what power? 2 squared. What do I do to root 2 to get 2? I square root 2, right?
Yeah.
So I would have to square that and square it again, which would give us to the 4th power. Does that make sense? Root 2 times root 2 is 2. So I do that twice, multiply that together to get 4. Yeah, that would be to the 4th power. So this would be 4. The next one's not so bad because I have the natural log, which is log base e. So I just have to rewrite e to the square root of e to some power. So that's the natural log of e to what power? To the 1/2 power. So my answer would be 1/2. I like the next one. Bingo. Bingo. Log base 5 of 5 to what power? 5 to what power gives me 1? 0. So that kind of leads us into something you need to know and have stuck in your memory. And remember this for everything in the future. The log of 1 is 0. No matter the base. The log of 1 is 0. Log base 10, log base 3, log base 5, log base e. Any logarithm of 1 is 0 because it works just like that. Okay? So that's something you need to have memorized. It is one of those things. There are certain facts and certain things you should have memorized. That's one of them you need to know. Okay? You need to know that if I'm taking the log of 1, I've got 0. That's what it is every time. Okay, now these ones, some of them you need a calculator for, some of them you don't. Okay. Now, the first one really is, you have log base x. That's the tough one. There's no getting around that. There's no getting around that. Log base x is a tough one, but it's really not too bad. Loop it. Rewrite it as an exponential. X squared equals 64. X equals 8. Why not minus 8? Because isn't negative 8 squared also 64? Try to take the log of negative 8.
Non-real answer.
Yeah, it doesn't work. And here's why. If you stop and think about it, okay, this is what an exponential function looks like. Okay. The inverse of an exponential function, if we were to copy this and draw it through the line y equals x, would look like that. Exponentials and logarithms are inverse functions. Your exponential will never be negative. So your y's, you will never get negative y values out of an exponential. Remember, the range of your function is the domain of your inverse. So that means our x's, if our y's will never be negative on the first function, the x's will never be negative on the inverse function. The other thing is your exponentials will never be 0. You cannot take the logarithm of 0 either. So you cannot take the logarithm of a non-positive number.
So you just
Right. So if you end up getting a log of 0, that doesn't work. You get the log of a negative number, doesn't work. Normally, we would say, oh, x equals plus or minus 8. We need to ignore the negative on that because it won't work in the original problem. Okay. Next one. Your same first step. Loop it. Rewrite it as an exponential. 3 squared equals 4x minus 7. That's not bad, right? So that means that's 9. So add 7 to both sides. 16 equals 4x. Divide by 4, x equals 4. Now here is something you have to do. We cannot take the log of what? A negative or 0. Take your answer, plug it back in the original problem. If we take 4 and plug it back in the original problem, will we get a negative number? No, so we're good. But you do have to check your answers. This is ones where you will get answers that don't work. You need to check. You get extraneous solutions. There you go. That's the phrase I was looking for. Some extraneous solutions might pop up. Take your answers, stick them in the original problem, make sure they will work. Make sure your original is not negative. You're not taking the log of 0 or a negative number when you do this. Okay. Same thing on the next one. Loop it. So this one, and I'm going to change the sign. Well, actually, no, I can do this just fine. So I have 5 squared equals x squared plus 4x plus 4. Yes, that is x plus 2 squared. And you can actually do this in several different ways. You can solve it. If you solve that was x plus 2 squared, rewrite it as x plus 2 squared, square root both sides, solve that. But you kind of miss out on a little bit when you do that. What you really want to do is set it equal to 0. So 5 squared is what? 25. So I'm going to subtract 25 from both sides. 0 equals x squared plus 4x minus 21. 0 equals 2 numbers that multiply to give me negative 21 that add to give me positive 4. 7 and negative 3. So that means x equals negative 7 and 3. Will they work in the original problem? The 3 will, and the negative 7 will too, because when I take negative 7 and square it, I get 49. And then minus 28, it's still positive. So both of those will work, but you do need to check. Both of those will work. Yes?
If you give us a problem on the quiz or test where the x squared is like a negative and it would be a negative number, so you have to cancel out the negative solution.
If you have it on your homework, because I'm not sure it pops up today. It does not pop up today, but it will pop up on notes coming up.
All right.
So the notes coming up, I know it does because I work through all the notes. And I know on ones in the future it does. It doesn't come up on today's notes, but I want to plant that seed for checking your answers.
All right.
Check them on the homework. And you should always check anyways just to make sure. And note, you do have your quizzes coming up Wednesday for you guys.
This is not Tuesday.
Okay. Okay, so these ones are a little bit different. These ones you do need your calculator for, but it's not that bad. So there are 2 ways of looking at how to do this problem. I can loop this problem. That's not how I like to look at these. I don't like to look at these and, ooh, I'm going to rewrite it as an exponential. What I like to look at is, okay, I'm going to take the log of both sides. That's the way I like to think about doing this. I could rewrite it, or I could take the log of both sides. Okay. Now, if I take the log of both sides, I would take the natural log of both sides. Why do I want to do the natural log of both sides? Because it's e. If it was 10 to some power, I would take the common log. Anything else, I'm going to take the natural log of. Okay? But because it's e, it works out fine. So when I have the natural log of e to some power, it is just that power equals the natural log of 5. And remember, the natural log of 5 is a number. It's just a number that is not, it's not anything special. Natural log is just a numerical value, so we treat it as if it was 2x equals 5, or 2x equals 3, or something like that. What do? Divide both sides by 2, and you get x equals the natural log of 5 divided by 2. Do that on your calculator. And by the way, I want to see how many of you get the wrong answer. Ooh, there's one. We got it right. And somebody who got it wrong.
Oh, I got it.
0.8047. Generally with logarithms, the rule is 4 decimal places with logarithms. But 3 is actually okay with me. If you did the natural log of 5 divided by 2, typed it all in at once, here's what happened. Your calculator took 5 divided by 2 and then took the natural log of 2.5. That's what happened if you did not get that. Your calculators, generally speaking, particularly with the graphing calculators, this is how they work. You type it, you hit natural log, and then you type in something, it will take the natural log of everything you type in after that. So if you do the natural log of 5 divided by 2, it does not take the natural log of 5, divide that by 2. It takes the natural log of 5 divided by 2, so natural log of 2.5. How do you fix that? Well, what I usually do, just to have it on my calculator, is I do the natural log of 5 equals, then divide that number by 2. What you could do is do parentheses around the natural log of 5, and then divide that by 2, and that will give you the same thing. You must be careful how you punch them in. Okay? You must be careful how you put them into your calculator, because it will. Your calculators are stupid. They do exactly follow the order of operations. The order of operations would say, hey, I need to divide before I take the natural log. Ooh, I'm taking the natural log of whatever follows. Unless there's parentheses around the natural log of what follows, then it does what's only inside the parentheses. So you have to be careful. Okay. What do I need to do first on the next one? Divide both sides by 4. I want to get e to the x plus 1 by itself first. So you just divide both sides by 4. And so I get e to the x plus 1 equals 5/4. And if you wanted to write that as 1.25, that's okay, because you're going to come out with decimals anyways. I almost always leave things undone. I do not start doing them on my calculator until my final step.
For the ln,
Yes.
if it's the natural log, why isn't it n?
Because it's a logarithm.
Natural.
Yeah. No, I mean, it's called the natural log because it uses e. That's what we call it, but it's L because it's a logarithm.
I know, but like
I don't know. Other than that, no. Because it's ln just because it's L because it's a logarithm. The logarithm is the most important part. So then we want to take the natural log of both sides. So ln of e to the x plus 1 is x plus 1. E is equal to the natural log of 5/4, and then subtract 1. So x equals the natural log of 5/4 minus 1. And this is another one you have to be careful what you're doing on your calculator. Take the natural log of 5/4 and then subtract 1. That's what I would do. Notice I didn't take the natural log of 5/4 and then subtract 1 from both sides. I worked it out. I left it like this. Okay. And you end up getting for this one, x equals negative 0.7769. Logarithms can be negative. You cannot take the log of a negative number, but you will get a log. You can get a log of something that will be negative. If what you're taking the log of is a number less than 1, you will get a negative number. Because For example, with e to the 0 is 1. Anything larger than that has a power larger than 0. Any number smaller than that, when you take the log of it, has a number power less than 0. So you will get negative logarithms. You cannot take logs of negative numbers. Questions so far? It's not that hard. Like I said, get used to the natural logs. Okay. So, word problem. Psychologists sometimes use the function, and I talked about how you can find the exact answers without graphing. And graphing, like I said, graphing, you got to remember, will not always give you the correct answer. We ran into that on a couple of the problems that we did in Chapter 1 when you were using your graphing calculator to find things. When you trace on your graphing calculator, remember, it's dots. It jumps from dot to dot to dot to dot. It's not a continuous line. It may look like it, but it's not a continuous line because computers cannot work in continuous functions. They work in discrete. They are nothing but a series of dots connected together. They're just really, really close. They look like it's one solid piece, but they are just a bunch of pixels or dots. That's how they work. They have to. Okay? When you work digital, it doesn't work as continuous, but it looks that way. So when you're doing a trace function, you might actually not be able to get the exact value you want for your y because it might go from one dot to the next dot, and the one you want is actually between those two dots. So you have to be able to know how to solve without using your calculator to solve them, and that's what we're going to work on today. Okay. So psychologists sometimes use the function L of t equals a times 1 minus e to the negative kt. Because you measure out the time, to measure out the amount L learned at time t. The number A represents the amount to be learned. The number K measures the rate of learning. So the idea is if you are learning a specific task, okay, the amount L is what you've learned of that task. A is where you started at. K is the rate of learning for that task. T is how much time has passed. Okay, some of it's for the individual. Some people, there's a general one you can get for people generally learn at this task at this rate, and they can apply how much you should learn after a particular period of time. You can also tell from that whether or not you really understand what's going on or not. Okay. Suppose the student has an amount A of 200 vocabulary words to learn. Psychologist determines the student learned 20 vocabulary words after 5 minutes. So you spent 5 minutes studying, and you learned 20 of the vocab words, the 200 you need to know. Okay, this makes sense. This is going to strike home with many of you, right? Okay.
5 minutes.
Yeah. So, how do you set this up to figure out your learning rate? That's what we're talking about. The first part is what is the rate K that you learn at using this information. So, L is how much they have learned. How much have they learned? They've learned 20 words. They've learned 20 vocabulary words. So 20 equals how much are they trying to learn? 200. Times 1 minus e to the negative kt. But we know what t is. What's our t? 5 minutes. So this would be negative 5k, because we take t, replace it with 5. And then what do? We move it up front because we want our numbers in front of our variables. That's for part A. Figure out the rate of learning for that particular student. Okay, figure out the rate K. Solve for K. It's not that hard. First step, divide both sides by 200. And you get 0.1 equals 1 minus e to the negative 5k. Subtract 1 from both sides. Negative 0.9 equals negative e to the negative 5k. And here's our first problem. I have negative e. I need to have positive e. Now, a lot of people would want to take the natural log at this point anyways, but I still would have a problem because I'd be taking the natural log of both sides, and I would be taking the natural log of a negative number. We're not allowed to do that. So, make them both positive. Multiply both sides by -1. That's the case may be. Now you take the natural log of both sides. And you get the natural log, and I'm going to switch the size on this one. So the natural log of e to the -5k, you get -5k equals the natural log of 0.9. Divide both sides by -5, and I get k equals the natural log of 0.9 over -5. Hey, use your calculator. You don't know how lucky you are. Old people like me, we didn't have calculators who did that. 0.0211. That's your K. That's the learning rate. Okay. Questions so far? Next couple of parts are actually, the next ones are actually pretty easy. Okay, we know the learning rate. You just take that rate, put that in, and you plug in 10, and you plug in 15 for T. The amount learned is equal to 200 times 1 minus e to the -0.0211 times 10. Question? Yes.
So why is your answer for last one? Why is it positive?
Okay. Take the natural. Yeah, but what's the natural log of 0.9? That's a negative number. If you're taking the natural. If you're taking the logarithm of a number less than 1, that number is negative. So yeah, it is. It is supposed to be a positive value there. It doesn't look like it, but when you're taking the log of a number less than 1, you get a negative. Okay. Yeah, so the next one for part B, that's easy. Plug in, you know what your rate K is now. We just solved for K. K was 0.0211. Plug that into the original equation along with the 200 for A, and plug in 10 for time, and you just work it out in your calculator. Do the e to this power first. Do you know where the e button is on your calculator? The natural log key. Look at the natural log key. The e to the x is the one above that. It's that shift. You have to hit the second key to get to it. Okay? And it's strictly a matter of plugging them in and working it out. And you get, at 10 minutes, they get approximately 38 words. Woohoo! Nope. What? Yeah.
That's a plan. Dude, this is a photograph.
Yeah. Do the stuff in the parentheses first before you multiply that times 200. You should get 38 for that one. And that's at approximately 38. I rounded off to the whole word. Approximately. Little squiggly. Squiggly. You've never seen that? Okay, this. I know, it's kind of bad.
Yeah.
That's approximately. I know it's really badly done. I got a little fatty marker, okay? It's not like I got a little tiny little highlighted pen, although my handwriting's so crap anyways. If any of you were actually looking at my notes. But yeah, that means approximately. So it's about approximation.
Okay, 0.7.
Okay, so the next one. Same idea, but put 15 minutes in for the time. How much did they learn of the 200 words they have to learn if they've been working at it for 15 minutes? approximately 54 words. So this is exponential growth because it is not growing at a continued rate. In 5 minutes, they learned 20 words. In the next 5 minutes, they learned 18 words. And the next 5 minutes after that, they went from 38 to 54, which is how much? 16. Got a phone call from a credit card company that I don't have a credit card. Well, let's set it up. So for the last one, you got to set it up. 180 equals 200. 1 minus e to the negative 0.0211 t. And this is one where knowing how to solve it using exact values is extremely helpful. But you do the exact same thing you did on the first problem, only you're solving for t instead of for k. It's exactly the same steps. Divide both sides by 200. Oh, there's my word. So you end up with 0.9 equals 1 minus e to the negative 0.0211 t. Subtract 1, negative 0.1 equals negative e to the negative 0.0211 t. Multiply both sides by -1 to make them both positive. Take the natural log of both sides. Natural log of 0.1 equals negative 0.0211 t. T equals negative, 2 equals the natural log of 0.1 divided by negative 0.0211. And you get approximately, I got 109 minutes. And I got yeah, well, it's an exponential decay. The more you do, it's going to take you. In theory, you're never going to learn all the numbers or all the words. You're going to get down to words less and less and less between what you don't know and what you do know. It's the idea behind it when you have a goal like that. In theory, but in reality, yeah, eventually we'll get that last little bit. Questions? I really got this down because I want to stop, and when I hit stop, it's going to cover everything up.
It stopped. All right, can I make a weird noise? Can I hear myself in recording?